Oh my goodness, I didn't know I was that much late. Goodness gracious. 22 minutes late getting started, sorry. No, it ate that much time, but it did. All right, and now I'll take more time. Are either of you in a first mini-term course? Yeah, do you know if Josh is? Okay. If you know of anyone who is, on Tuesday night, they open the spring course, the evaluation for first mini-term courses. And then they send us an email saying, no, none of your students have responded yet. You know, within minutes of opening it up, they said none of them have responded. Well, yeah, I mean, how could they respond if you just now opened it? So anyway, if you know of anyone who's doing a first mini-term course, because they do it on such short notice, they may not know that that's been opened. So tell them that they can do their student course evaluations. Okay. Now, and sorry about this. This is a mess next week, and this week, the rest of it is a mess. I'm out of town tomorrow, so I won't be on the Birmingham campus tomorrow again. And so normally I'm there 8 to 12. I won't be on either campus tomorrow. I'll be on the road. Okay. So that's tomorrow. Next Tuesday, this class is supposed to start at 11:30. I hope to be back by 11:45. If everything goes perfectly. I've got a doctor's appointment, and if he sees me in time and I can get out and everything works well, I hope to be back by 11:45. Okay? If not, it may be 12, and hopefully it won't be any later than that. But whenever I get back, I'll come up here and I'll continue where we left off today. Okay? Now, Thursday, I'm in Tuscaloosa because that's when they scheduled me to have a meeting there on the retirement. We have to have a meeting, and they don't schedule them on Fridays. And they said, pick your town. I said Tuscaloosa. They chose the date, and I'll be there on Thursday. So I won't be on campus at all. Well, I say that. The meeting gets over with sometime like 3:30 in the afternoon, so maybe by the time I drive back, it'll be 4:30. I'll be here for maybe an hour, hour and a half, okay, and late in the day. Okay, so that's Thursday. Friday, I think I'll be on the Birmingham campus. That's next Friday, not tomorrow. Pretty much 8 to 12. I do have a dermatology appointment in the afternoon, but I don't remember what time. If it's any time after 12:45 or 1 o'clock, then I won't miss any office hours. But if it's before that, I may miss 15, 20 minutes or something like that. So anyway, it's a crazy week next week. All right, well, oh yeah. Because this is ending the first mini-term next week, we're beginning second mini-term next week, which means we're at midterm, I think Wednesday at midnight, or sometime like that. And usually after midterm, they ask for midterm progress reports, which I don't think we got any progress in this class. I got yours from the other class. I haven't got a research paper or the first test yet. So please get those in. One of them, at least one score in sometime next week, if possible. Because those midterm progress reports are usually the next week after that. So try to get me something then. All right. Let's go from the current slide. I thought I had already done that. Here we go. Okay, I can't think of anything else. Do you have any questions? Okay, sorry we're so late getting started. All right. Where we left off last time, we had been using elementary matrices, and because, of course, your elementary matrix is one step away from your identity matrix. Your identity matrix is, of course, an invertible matrix, and you do a legitimate row operation. It's still, so your E is an elementary matrix, then it's invertible, okay? And since it's an elementary matrix and the this inverse exists, that's also an invertible matrix. So both E, that's what we call an elementary matrix, if I can get the pen to come up, there we go. Both E and E inverse are invertible. Okay, that basically is theorem 2.7. If E is an elementary matrix, then E inverse exists, meaning E is invertible, and E inverse exists, and is also an elementary matrix. Now, Josh, did you follow anything enough to know what an elementary matrix is?
Yes.
Okay, got it. Okay. It's one step from one elementary row operation from an identity matrix. Okay? So, the inverse of an elementary matrix E is the elementary matrix that converts E back to IN, because when you multiply it. So, here are some for instances. Okay? I'll go and start with a clean sheet here. All right. Here's an elementary matrix they're calling E1. You verify whether it is. Excuse me. Excuse me again. First, is that an elementary matrix? They say it is. Yes. You just exchanged two rows. Okay? What would be its inverse? Any ideas? I'm sorry? I'm teaching, yeah. Okay. Probably ought to close the door. I'll be teaching until 11:45. Is that right? Yeah. 12:45. Huh? Yeah, I know. But I mean, we're going to be having class in here. You okay with that? Okay. All right. What is the inverse of that matrix? Okay. It gets to the identity matrix. If you multiply this matrix by the identity matrix, you get this matrix again. But you want the inverse of this matrix gets this matrix back to the identity matrix. So what would it take to do that? Exchange the same two rows again, right? So the inverse of this is the same matrix. Oops. Okay? Let's verify that. Okay? Because if you multiply a matrix by its inverse, you should get the identity matrix, right? So let's see if we do. 0, 1, 0. So that gives you a 1 right there, right? Then you get a 0, 0, 0, 0, 0, 0, 0, 0, 0. This one. 0, no, 1, 0, 0, 1 in the middle, that's good. 0, 0, 0. So far, so good. Last row, 0, 0, 0, 0, 0, 0, 0, 0. Yeah. So, how this elementary matrix came from reversing these two rows in the identity matrix. The one to get you back is to reverse the same two rows, which that would be the same elementary matrix. That would be that. Okay. Here's another, or at least they claim it's an elementary matrix. Let's verify that too. 1, 0, 0, 0, 1, 0, and negative 2, 0, 1. Now, is that an elementary matrix? Yes. How did you get it? Got it. Yeah, you did negative 2 row 1 plus row 3. Got it. So that's a single elementary row operation. Produce elementary matrix. Now, what would be the inverse of that one? E2 inverse. What would you have to do to this one to get back to an identity matrix?
You look to positive.
Okay, well, yeah. But what operation would you have to do to this one to get it back to become an identity matrix? Okay, let me make sure I'm saying that right. The inverse of an elementary matrix E is the elementary matrix that converts E back to IN. So you're wanting to take this to go back to an identity matrix here. This row is 5, that row is 5. What would you have to do to the top row to get this to become, what would you have to do to get this to become identity matrix? In other words, if you're going to row reduce that, what would you do?
Negative 2, 0.
How?
Do row 2 times row 1 plus row 3.
Yeah. Okay. So what elementary matrix does that? All right. Okay. Perfect. You see? That's what the inverse matrix does. And if you wanted to multiply those out, you could see if indeed you get what we want to get. I think you do. Okay? So E3, or at least they claim it's an elementary matrix. Let's see. 1, 0, 0, 0, 1, 0, and 0, 0, 1 half. Is that an elementary matrix? Yeah. Okay. What would be its inverse? One, 0, 0 sounds good to me. 0, 1, 0 sounds good to me. 0, 0, 2. Yeah, you need to multiply this row by 2 to do that to the identity matrix, and that would be that. So indeed, that's what you got. Okay? And then you can do matrix multiplication to see if that's what you get. And we did on the first one. I don't want to do it on every one, if it's okay with you. All right. Now, here comes another theorem. It sounds a lot like other theorems we've done. A little bit of a difference. A square matrix A, okay, is invertible if and only if it can be written as a product of elementary matrices. Okay, now that sounds a lot like something we've already done before. I guess we haven't quite done it. What we did before was if A and B are both M by N matrices, matrix B is row equivalent to A when it's a series of elementary matrices multiplied by A. Okay. This isn't quite the same thing. This is saying a square matrix A is invertible if and only if it can be written as a product of elementary matrices. So every invertible matrix can be written as a product of elementary matrices. Now, they go into the proof, and you prove it one way, and then you need to prove it the other way as well. Those usually take a little more time, but they do it in about 3 paragraphs, so I would definitely read that and make sure you understand what they're talking about. So let's do this. Let's do example 4, and we'll actually do one. Now we're going to do a real easy one. 2 by 2. Okay, here's matrix A. It's -1, -2, 3, 8. Okay, it says find the sequence of elementary matrices whose product is this non-singular matrix. Now they say it's non-singular. How can you quickly verify this non-singular matrix? In other words, it's invertible. Only because it's a 2 by 2 can you do this quickly. It's what?
As a identity matrix.
Okay, yeah, that's what you're going to get toward. But the thing is, how can you verify this is non-singular? Almost just by looking at it. You have to do 3 operations and you got it done. And it's all one step, one operation, 3 steps. Remember? 2 by 2s?
How do you do the fundamental?
Not how to find it. Just tell me that whether it's invertible or not.
You do 1 times 8 and
-1 times 8 is -8.
and then plus
6.
minus 6 is
-8 plus 6 is?
-14.
No. It's -8 plus 6. Up diagonals and the opposite of that. -2. What does that tell you? It's invertible. If it's not 0, it's invertible. And that determinant is not 0. So we know it's invertible. So what we need to do is find a sequence of elementary matrices whose product is this. Okay? Okay. Now, here's what we do. We know how to do this. You just augment that with the identity matrix and do it. But that doesn't give you the series of elementary matrices, the product of elementary, sequence of elementary matrices whose product is this matrix. Okay? So here's how we do it. We almost do what we were doing before. If you were going to row reduce this, what would be your first step? Yeah, you negative row 1 is the new row 1. Okay? So, that would be 1, 2, 3, 8, right? Just negate the first row, because you want a 1 up there. Now, what elementary matrix does that same thing? Now, I'm going to write up here 1, 0, 0, 1. That's your identity matrix. What elementary matrix does the same thing to this identity matrix that did to this one? Negative 1, 0, 0, 1. Yeah. Okay, so that's your E1. Okay? Now, what's the next step you would do? How? Got it. Okay? And what would that produce? 1, 2 stays the same. 0. 2. That stays the same. So that's the next step. Now, what elementary matrix? Remember, don't operate on the previous elementary matrix. Do the same thing to the identity matrix up there that you did here to that matrix. And what would that be? 1, 0, negative 3, 1. Perfect. Okay? Now, okay, I also wanted to do, I thought I did, but, okay. They're not doing this in the book, I'm doing it. What is the inverse? Let's go back to that first one. What's the inverse of that matrix? Same thing. You're absolutely right. Okay? That would just change it back. Yeah. To, okay. What's the inverse of this matrix? Perfect. Okay? All right. Now, what's your next step down here to this one? Go back to this one. Row 2 divided by 2. Okay, it becomes a new row 2. Okay, so that would become what? 1, 2, 0, 1. Okay. Now, what elementary matrix does that same thing? 1, 0. Say again. I couldn't hear. 0, 1? Oh, 0, 1 half. Okay, got it. I can't hear. Okay? Absolutely. Okay? Yeah. No. Yeah. Okay. I'm doing the next one. Okay. What's E3 inverse? 1, 0, 0, what? 2? Perfect. Okay. All right. Didn't plan well. I'm running out of room. What's the last step that you do to get this to be the identity matrix? This is so bizarre. It writes it, and then I write something else, it takes it off. Okay. Yeah, that's what you did. And what does that give you? 1, 0, 0, 1. So you're done here. What's the elementary matrix that did that same thing? 0, 1. Perfect. And what's the inverse of that elementary matrix? That one we just did. Wait. Okay, yeah. So again, 1, 2, 0, 1. All right. Nice little exercise, right? But does that give you a product that produces that matrix? Yes, it does. And here's what that is. This A that you have here is the product of, okay, E1 inverse, why it's not showing up, times E2 inverse, times E3 inverse, times E4 inverse. Okay? That's what they claim. Okay? Now, I guess I shouldn't have written that. Let me go back. Okay? I need to justify it better than I just did. Okay? I jumped the gun, so to speak. All right. Now, if you think about what we just did, okay, remember what we did last time. This operation, okay, following this operation here, that first operation we did, remember? This first operation here was if we had multiplied this times this on the left-hand side, remember? That gave us this very operation. So what we did here, we took A and multiplied on the left by E1, right? Yay or nay? Okay. And then the next operation, we multiplied that matrix by E2. And then the next operation was equivalent to multiplying that matrix by E3. And the last one was multiplying that by E4. And that gave us the identity matrix that we got down here. Right? Now, how do we undo that? Okay? If we do an E4 inverse to the left of that one, we would do, and if you don't mind, I'm going to scoot this I over as far as I can here, okay? So if I do a E inverse 4 here, do an E4 inverse there, okay? Now this becomes the identity matrix, so you can sort of toss it. Now you take that and multiply it by E3 inverse, so you have to multiply here by E3 inverse. And by the way, you can throw away the I too, because that's not doing anything, it's just reproducing. And now these two becomes an I, you can throw that one away, and then multiply by E2 inverse. And that would multiply this by E2 inverse. And then these become an I. You can throw that away. Yuck! And then finally multiply by E1 inverse. multiply this by E1 inverse, and and this becomes an identity matrix. So here we have A is equal to this. You can throw this one away because you just multiply by 1. Okay? So that's how we get that this matrix A is the product of, goodness gracious, is the product of E1 inverse, E2 inverse, E3 inverse, and E4 inverse. Okay. Now, I guess maybe that we ought to verify that, but I don't know that that's necessary. Now, do you want to? Do you want to verify that? Sure. They didn't in the book. I just wondered if you have a hankering to. Okay. Well, take their word for it that that is indeed true. Okay. Now, if that wasn't bad enough, what if you multiply both sides of that equation by your A inverse? Okay? Oh, wait, I'm sorry. I think I'm just going to have to erase because I'm out of room. Okay? I don't think I need anything. They're going back to a generic form now. Okay. Back in section 2.3, we learned the process of finding an inverse for a non-singular matrix by using Gauss-Jordan elimination. And we did A augmented with I, and we did our various operations on it to get to I augmented by A inverse. Remember? That's what we did. We did our elementary row operations. Okay. Now, using 214, which we just did a little bit ago, you can write this as a product of elementary matrices, and what we just did, if we write the I, and this is backing up and doing what we just did before. Now this is a generic matrix, so it's not just a 2 by 2 we did before. E sub k, if you had k steps in there, k elementary matrices, times E sub k minus 1, times E sub k minus 2, dot, 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 multiplied together until you get down to E sub 3 dot E sub 2 times E sub 1, and that's multiplied by A. Okay. Now, that's what we did in the last. We only had 4 before. But if we multiply by the elementary matrix 1, 2, 3, and 4, we wound up with the identity matrix, right? That was our method of row reduction from before. This is saying you can do it for any square invertible matrix. You can do that. Okay? Now, if you multiply both sides of this equation on the right by A inverse, so do A inverse here and multiply that by A inverse, okay? And well, I don't know. It just seems like they're going in circles here. We've already done what they did without. I don't know. Anyway, that last part of that paragraph seems like they're just going in circles. So I'm going to not do that. Let's just go down to Theorem 215. Here are equivalent conditions. We've had the first 4 of these before. We're adding a 5th one now. Here it is. If A is an n by n matrix, if it's not square, don't even try, okay? Okay, n by n matrix, okay? Then the following statements are equivalent. All these are equivalent. If A is invertible, okay? Of course, if it was n by A, it couldn't be n by n, it couldn't be invertible. But if it was n by n and it is invertible, then all these others are true. Okay? For instance, this one. AX equal B has a unique solution for every column, matrix column B. I said it backward column matrix B, or vector V. And that, by the way, is an n by 1 column matrix or vector B. Okay? For every B you put out there, you can find a unique solution. Okay? Now, a consequence of that, if AX is equal to 0, and frankly to me, that had better be the 0 vector, okay? The n by 1 0 vector. They don't list it that now, but, well, no, it can be 0, I guess, okay? It has only the trivial solution. And that basically comes from the previous, because the previous said it has a unique solution for every vector B. Well, the vector 0, 0, 0, 0 has many zeros as you need, n of them. That has to have a unique solution, and since the trivial solution will always produce that, that is the only solution you have. Okay? 4. A is row equivalent to IN. And we got that because that's how we determine the inverse. You do the row reduction until you get the IN. If you don't get the IN, it doesn't have an inverse. Now we add the 5th one. A can be written as a product of elementary matrices. That's the one we just did. Okay, now, notice I started with this one. The A was inverted, and we derived all the rest of it from that. But you can start with any one of these and derive all the others. So if it can be written as a product of elementary matrices, that means it is invertible, and that means all these others are true. If it's row equivalent to IN, that means it's here, exists, all these others are true. Any one of these means that all the rest of them are true. Okay? And remember, it only is for square matrices. All right. Now, it seems like they're jumping a rabbit here, and they kind of are, but it's getting to something. Now, you probably aren't into doing algorithms for solving matrices yet. But if and when you ever get there, at the heart of the most efficient and modern algorithms for solving elementary systems of equations, AX is equal to B, is a thing called the LU factorization. So if you're trying to solve AX equal B, now remember we've seen several examples of this. Your scheduling of flight crews, and flights and things like this. Those are set up by enormous matrices, okay? And you're trying to solve one of those, okay? The most efficient way to do that is what they call the LU factorization, in which a square matrix is expressed as a product. So this A here is expressed as a product of a L times a U. Now what in the world is the L? The L is a lower triangular matrix. What is U? An upper triangular matrix. Okay? Now, what do we mean by that? A lower triangular matrix looks like this. I'm going to do it for the 3 by 3 case. They have to be square, by the way. A11, 0, 0. A21, A22, 0. A31, A32, A33. That is a lower triangular matrix. Why lower? Because everything above the diagonal is 0. Everything above the diagonal is 0. Certainly the diagonal isn't 0, and the things below it, I guess, could have some zeros in them, but this is a lower triangular matrix. And on the other hand, what is an upper triangular matrix? That would have an A11, A12, A13, 0. A22, A23, 0, 0, A33. Now this is just for a 3 by 3s. 4 by 4, 7 by 7, n by n. Everything below the diagonal, above the diagonal being 0 makes it a lower triangular matrix. Everything below the main diagonal makes it, being 0, makes it an upper triangular matrix. So, if you can find a lower triangular matrix, but when you multiply it by an upper triangular matrix, you get the matrix A. You then said you factored that matrix A into LU, lower times upper. All right. Now this is 3 by 3. Here it is generically for any size. Okay? If an n by n matrix call it A, can be written seems like they tell you what it is and they give you the box with the definition which repeats exactly what they told us. Can be written as the product of a lower triangular matrix okay, L, and an upper triangular matrix U, then A is equal to LU is an LU factorization of A. Okay, the factorization, because it's two matrices multiplied together, gives you A. It's a LU factorization because the first matrix is lower and the second matrix upper. Okay, now we're going to do example 5, which we don't have to do anything to get it, they're giving it all to us. Okay? I'll start it the other way. 1, 0, 1, 1. I'm going to multiply. And by the way, is that a triangular matrix? Yeah or nay? Anybody? Is this a triangular matrix? Or not?
Because when it don't have to be 2 zeros.
Nope. All it needs is find the main diagonal. There it is. Everything above it is a 0. Only one thing, right? Okay? And what kind of triangular matrix is that? Because everything above it is 0, it's a lower triangular matrix. That's an L. Okay? Now we're going to multiply it by another matrix. Here it comes. 1, 2, 0, negative, 0, negative 2. Okay. Is that a triangular matrix?
No,
Why not?
because it doesn't have to have a 0 above it, and it doesn't have a 0 above.
Find the main diagonal. 1, negative 2. Every element below that is a 0.
Okay, yes, so it is.
So what kind is that?
Upper.
Second?
Upper.
Yeah, okay. Take them. No, I'm sorry. That's not the kind of uppers. Okay. So this is an upper triangular matrix. Okay. What happens if we multiply those two matrices together? Can we do that? What is it? 1, 2. Okay, quick. 1, 0. Okay. Now that's some matrix A. Okay? And what we've just done, we didn't do it, the book gave it to us. This A is factored into L times U. That is an LU factorization. So that's your L, that's your U. Okay. Now, the B is going to take a little more effort. Okay? So let's do B. One zero zero 0 1 0 no, I can't read. 0 1 3 no, I read right the first time. Okay, sorry about that. 1 0 0 0 1 0 2 negative 4 1. Okay. Is that a triangular matrix? Yay or nay? Why not? That's not all zeros on both sides. If you had all zeros on both sides, it would be identity matrix. It would be both upper and lower triangle. But this, find the main diagonal. All these entries are 0. Not all these are. So this is a, no, the zeros are up here, lower triangle matrix. So that is your L. That is an L, okay? An L. And you're going to multiply that by this matrix here, 1 negative 3 0 0 1 3 and 0 0 14. One of my favorite numbers in the world. Okay, now, is that a triangular matrix? Okay, which kind? That's an upper, okay. Now, can these be multiplied together? They're the same size, so of course they can. What does that give you? 1 in the first one, that's pretty easy. Negative 3, 0. Okay, that stayed the same. 0, 1, 3. And 2. Negative what? 10. Let's see. It's negative 6. I'm lost. Okay, yep. Negative 6 minus 4. Negative 10. Yeah. And 2. Okay. Let's see if that's what they got. Yes. Okay. That is some matrix A. And this matrix A is written as a product of a lower times an upper triangular matrix. That makes it the, whatever you call it, the LU factorization of matrix A. Now, there is a linear algebra applied at the bottom. I don't know if either of you are planning to go into fluid dynamics. That's probably part of mechanical engineering, I would think. There could be parts of others as well. But computational fluid dynamics is a computer-based simulation of real-life phenomena like fluid flow, heat transfer, chemical reactions, other things. And guess what? They use linear algebra to solve it. Okay? And you use all the tools at your disposal with supercomputers that can do massive number of calculations, and you can model lots of things. They say here aerospace companies like Boeing and Airbus have used computational fluid dynamics in their aircraft design. Okay? Please don't tell me that they used it on the 737 MAX. I don't think they did well. Okay, but we won't go there. That wasn't what they were talking about. All right, top of page 80. How are we doing on time? 1 minute. Let me just read this to you. If a square matrix A row reduces to an upper triangular matrix U using only the row operation of adding a multiple of one row to another row below it. No multiplying by a constant, no swapping two rows. If you can do it in just multiplying, adding a multiple of one row to another row, then you can find the LU factorization. That's what we'll do with example 6, and we will begin there next time. Okay, let me give you a few homework exercises. Oh, we came close to finishing 2-4, even though we got started way late. Any of the odds 1 through 7, they're all at Calc Chat. 9 or 11, they're both at Calc Chat. Any of the odds 13 to 17, they're all at Calc Chat. Any of the odds 19 to 23, they're at Calc Chat. 25 and 27 are at Calc Chat. 29 through 35 are at Calc Chat. And then there's some writing exercise 37. I don't know if that's a Calc Chat or not. If it is, you can look into that. 39 should be at Calc Chat, and 41 is a true false. That should be at Calc Chat. We haven't found the LU factorization yet, so you can hold off there and we'll pick up and go. Actually, number 43 is a lower triangular matrix to begin with, but that's beside the point. Okay. We'll see you Monday. Have a good weekend.
Hey, Dr. Collins.
Hey.
I have everything that you gave me yesterday in my paper to turn in.
Okay.
I have an appointment at 3:30 that I can't miss. And I know we have a test today. Is there any way that I could take that before or after?
What time do you have to leave?
At least by 2, because it's in Hoover, so that's kind of far.
Okay. Yeah, well, if you start at 1:30, you should probably be able to finish by 2. Good deal. Okay. Now, by the way, I won't have these graded by class time.
That's
Okay.
fine. That's
All
fine.
right. And in fact, I don't have everything graded because I got so much in so late